So this is the 21st session on rigid body kinematics. This is in continuation of the 22nd video, 20th video. So in this video also I'll take up a numerical problem on pure rolling. Okay. It will be a good question. If you go through it, your fundas will be very much cleared. Okay. So I'll first draw the diagram. Consider the diagram shown below, in which all the details are given. Okay. The problem is like this. This is a fixed inclined plane. This is our double cylinder. This is a double cylinder. Okay. C1 is the center of the double cylinder. Inner radius is R. Outer radius is 4R. There is an extensible string folded over the inner cylinder. This string is parallel to the inclined plane. And here it is folded several times on another cylinder, double cylinder, whose center is at C2. C2 is fixed. Radius is R. Outer radius is 7R. Now another inextensible string is folded on the inner cylinder like this, and this string passes over another cylinder. This string like this. Like this. This is another double cylinder whose center C3, and a string is folded on the inner radius of this cylinder is R. Outer radius is 10R. And here a string, inextensible string is folded on the inner cylinder, and string is continuous here, block is here, it is moving downward at a speed V. This inextensible string is attached to a fixed ceiling like this. So this is the situation. Okay, fine. Now here all the strings are inextensible. All strings are inextensible. C2 is fixed. C2 of this double cylinder is fixed. Here, this is a fixed inclined plane. Here, pure rolling takes place. Pure rolling takes place here. There is no slip at all points of string and the cylinders in contact. At all the points of string and cylinders in contact. All points of string and the cylinder in contact. Okay. C2 is fixed. C3 is not fixed. C3 of this double cylinder is not fixed. Okay, fine. The question is find VC1. Find the speed of center C1 of this double cylinder which rolls without slip over this fixed inclined plane. Okay. So this is what we have to determine. Alright, fine. So now all the strings are inextensible. Here no slip. Here also there is no slip. String and double cylinder in contact, no slip. Here also string and double cylinder in contact, no slip. Here also string and double cylinder in contact, no slip. Here also no slip. Here also no slip. Here also no slip. And here pure rolling takes place. C2 is fixed. C1 and C3 are not fixed. This string is folded over the inner cylinder and this block moves down at a speed v at the given instant. The question is, find Vc1 in terms of v. Vc1 has to be found in terms of v. Vc1 to be determined in terms of what? V. Vc1 to be found in terms of v. Okay. So now we have to find Vc1 in terms of v. Now to solve this problem there are two possible approaches. Either you start from this side and then move towards, come till here, or you start from here and move and come here. We can take any one of them. Okay. So what we'll do, we'll start from this side and reach till here, and then we'll get the final value of Vc1 in terms of v. Alright. Now we start from here. Now, so first thing, we must decide whether center C1 will move up the incline or down the incline. Now this problem is same to that which I discussed in the 20th video on rigid body kinematics. There was a similar question in the previous video, where I have explained at the end of the 20th video that there was a point C in 20th video, there was a point C, it should move towards right. That concept will be used here. So center C1 of this first double cylinder should move up the incline at a speed Vc1. Now this double cylinder undergoes pure rolling over this fixed inclined plane. So angular speed of this double cylinder should be in clockwise sense, say omega 1. Alright, fine. Now here, this is a point D1 of the inner cylinder which is in contact with the string. There is a point D1 of the inner cylinder which is in contact with the string. Here also there is no slip, which I have said just now. No slip. So no slip in short we will write as NS. NS meaning no slip. Alright. NS meaning what? No slip. So now see. So first of all, we remove omega, we apply SRC between C1 and D1 in ground frame, okay? So SRC between C1 and D1 in ground frame. So selected point is C1, other point is D1. Okay. Now we join the line joining C1 and D1. This is C1, this is D1. We give the velocity of center C1 to D1, so we give Vc1. Now omega 1 of this drum is clockwise, as I have explained just now. So D1 moves in a clockwise circle with C1 as center and radius r. So for this, if D1 is to move in a clockwise circle with center at C1, we give a speed of omega 1 r in leftward direction. The velocity of D1 is the vector sum of these two. Now, one thing you can see, as this block will move down, this drum will rotate clockwise. So this string will move up. If this string will move up, then this point of string will also move up. Because here it is no slip, so D1 also should move up. So D1 should move in upward direction. So resultant of these two should be in upward direction. So this should be more than this. So we should write Vd1 is equal to Vc1 minus omega 1r. Okay. Now we have to remove omega 1. Now here it is pure rolling condition. Radius is 4r, center C1 is moving at Vc1. If we apply pure rolling condition here, then we get Vc1 is equal to omega 1 into 4r. So omega 1 into r is just Vc1 by 4. Okay. Omega 1r is how much? Vc1 by 4. That is omega 1r, Vc1 by 4. So this I substitute here, then I get Vd1. Okay. This is rubbish here, okay. So I substitute this one here. Velocity of D1 should be Vc1 minus Vc1 by 4. That is just 3 Vc1 by 4. This is Vd1. Alright. So Vd1 becomes 3Vc1 by 4. Fine. Alright. So this point of string which is in contact with D1 is moving up the incline at a speed of 3Vc1 by 4. Now this string is inextensible. So every point of this port segment of the string is moving at a speed of 3Vc1 by 4. So this point here, it is no slip. So this point of this second double cylinder is also moving at a speed of 3Vc1 by 4. Okay. Now this drum rotates clockwise at angular speed omega 2 for here to be no slip. Now C2 is fixed as I said just now. Let us call this point as D2. This point of this double cylinder which is in contact with the string here as D2. Now C2 is fixed and D2 to C2 distance is constant 7r. So D2 moves in a clockwise circle with center at C2 and radius 7r. So velocity of Vd2 from circular motion theory should be 7r into omega 2. That should be Vd2. So Vd2 is 7 omega 2r. Okay. And this should be same as Vd1 because here it is no slip condition. So from this we see that 3Vc1 by 4 is equal to 7r omega 2. That meaning r omega 2 is simply 3Vc1 by 28. This is r omega 2. So r omega 2 becomes 3Vc1 by 28. This is r omega 2. Okay. Now what we do, we consider no slip here at this point. Let us call this point as D2 dash. Okay. Now this C2 is fixed. D2 dash moves in a circle with C2 as center and radius r and angular speed omega 2. Therefore, V D2 dash simply becomes omega 2r from circular motion theory, which is simply 3Vc1 by 28. This is Vd2. So Vd2 dash becomes 3Vc1 by 28. Alright, fine. So this one are a bit, okay. So Vd2 dash becomes 3Vc1 by 28. Alright. Now see, here also string and the inner cylinder is in contact. Here also it is no slip. So this point of string in contact with D2 dash should also have a downward speed of how much? Same as 3Vc1 by 28. Now this segment of the string is inextensible. So this point of string in contact with this cylinder should also have a downward speed of how much? 3Vc1 by 28. Fine. Alright. So here it is no slip. So this point of the double cylinder in contact with the string should also have a speed of same 3Vc1 by 28, that is Vd2 dash. This point should also have the speed of this much. Now you see, in this one thing you see, as this block will move down, this string unfolds. So center C3 will move downward at some speed, say V3, which is not being given, I just assumed it. And this drum will rotate anti-clockwise at angular speed omega 3. Okay, fine. So now you see, so Vd2 dash is same as how much? 3Vc1 by 28. And this C3 moves at V3 and this block moves at speed V downward. Okay. Now the most crucial point is this. Most crucial point is this. See, at this point also the string and the double cylinder are in contact. You can see. The string and the double cylinder are in contact at this point. Now as the cylinder moves down, this string also unfolds here. Length of this vertical segment of the string goes on increasing. Length of this vertical segment of the string goes on what? Increasing. So at any instant of time, all the points on the vertical segment of the string are at rest. At any instant. So at this instant of time, all points of the string in this much vertical segment of string are at rest. So this point of string is also at rest. Okay. So now here also it is no slip. Between the string and the double cylinder, here also it is no slip. So this point is also at what? Rest. Alright. So this point is at rest. This block is moving at a speed V. Alright, fine. Now this block is moving at a speed V. Now the string is inextensible. So this string will also move down at a speed V. Here also it is no slip here. So this point will also move at a speed V. So now what I do, I take these three points. Slightly it has been drawn, slightly lower I have drawn. Okay. Now see, consider these points. This point, and this point. This point whose speed is 3 v/c by 28. This point whose speed is v, and this point whose velocity is 0. I consider these 3 points here. I draw this line here like this. See. So this point is just this point, which is moving at vd2 dash. That is 3 v/c by 28. This point is moving at a speed v down, and this point is at rest. Okay, fine. And this is how much? This is 10r. This distance is 10r. And this distance is 10r. This is r. So this is 9r. No, this is not 10r, sorry. 10r is this much plus r. It is 11r, sorry. 11r. And this is 10r. This is r. So this is how much? 9r. 9rc, like this. Is it fine? Alright. So this is how much? This is 10r and this is r. So 11r. And this is 10r and this is r. So this is 9r. Now, here also we can apply SRC as we have been doing here. But here again it is easier to apply the section formula. Because this point divides this line internally in the ratio 9:11. Okay. So I apply that section formula. So lambda becomes 9 and mu becomes 11. And this point, velocity of this point is written as, this is mu, this is lambda. So 9 times velocity of this point, which is 0, plus lambda times this plus mu times this. 11 times velocity of this point, 3 v/c1 by 28 by 11 plus lambda plus mu, 20. Here also we can apply SRC method, but section formula is better, so I apply section formula method here. From this I see that this becomes 0, 9 into 0 vector 0. So this means that V is equal to how much? 3 into 11, 33. 33 v/c1 by 560. Okay. So from this we can solve for v/c1. So if you solve this, how much v/c1 going to be? v/c1 is going to be 560 v by 33. 560 v by 33 is the required value of v/c1. So v/c1 becomes 560 v by 33, which is therefore the required answer. Okay, fine. So v/c1 comes out to be how much? 560 v by 33. That is the value of v/c1. 560 v by 33. Okay, this is the final answer. Okay, fine. So this was a good problem. Okay, if you solve such kinds of problems now, if you solve 4 to 5 such questions, you can at least solve 50 to 100 objective based on these 4-5 questions. So definitely, if you are preparing for JEE Advanced, you must try to solve these such questions. Then only you will have the speed, you will have the confidence, you will have the accuracy. Fine. So you must never run away from solving tough and lengthy problems, because that will give you the confidence, speed and clarity. Okay, that will be beneficial to you for all respects, so especially for solving problems of JEE Advanced. Okay, so this I close it here. Fine. Or just excuse me, sorry. I'll take one more problem on this case. So second chapter of rigid body kinetics will be finished hereby. All right. Now this I have it. Okay. This also a rabbit, okay? So I'll take up one more problem on this second chapter on rigid body kinematics, and then second chapter will be finished. So this was the biggest chapter on rigid body kinematics. Okay. I'll take one more problem. So again, I'll write here just to save that time for writing the question. Consider the diagram shown below. In which all the details are given. Okay. The diagram is like this. This is a double cylinder. C is the center. Inner radius is small r. Outer radius is capital R. This is a fixed horizontal surface. This is a double cylinder. Together they constitute a rigid body. String is folded on the inner cylinder several times. And here there is a fixed peg. Okay. And here the string is moving down at a speed v. This peg is fixed. It's a fixed peg. Alright. It's a fixed peg. String is, this is inextensible string. It is an inextensible string. And here pure rolling takes place. And here between the string and the inner cylinder there is no slip, which you write in short as no slip. Okay. And this vertical segment of this string makes an angle of alpha with the vertical. Alright, fine. Now question is, find VC in terms of V small r, capital R and alpha. Okay, this is the question. This is the question which we have to solve. Okay, fine. So this is the question, okay. And here there is no slip, and here also there is pure rolling over the fixed surface. We have to find VC in terms of V small r, capital R and alpha. So what is the approach going to be fundamentally? What is going to be a fundamental approach to solve such problems? What is the approach? That is the question. See, this is the inner cylinder. Let us take this point as, say, P1. Let us call the point of string in contact with this point P1 as S1. Okay. So now see. This point is moving, this end of the string is moving down at a speed v. String is inextensible. So this point S1 of the string, which is in contact with the inner cylinder, that is also moving at a speed v. Okay, fine, alright. Now see, one more thing. One more thing which has to be kept in mind is this. See, point is this, that first of all we have to find VC, speed of center C. Now again in this question, center should move rightward. Then only no slip and pure rolling can take, no slip here and pure rolling can take place here. So center C should move rightward at a speed VC. Also pure rolling is taking place here on a fixed surface. Center is moving rightward. So pure rolling, this drum should rotate in a clockwise sense with certain angular velocity omega say. Alright, fine. Now one thing I would like to say, see, here no slip is taking place. Speed of S1 is V. But we can't say that speed of P1 is also V. That we can't say. Reason? See, this will be V only when contact is maintained here. String and the inner cylinder. But as the time will pass by, the string will unfold from this. So contact between C1 and P1, S1 and P1 will not be maintained. So velocities of S1 and P1 along common normal will not be equal. Velocity of P1 and S1 only along the common tangent plane, that is along the string, they will be equal. Is it clear what I have said? Velocity of P1 and S1 along the tangent plane will only be equal. S1, velocity of S1 and P1 along common normal will not be equal. Why they will not be equal along the common normal? Because S1 and P1 will not always be maintaining the contact. After a short time dt later, S1 and P1 will no longer be in contact. So since they are not always be in contact, so along common normal, velocity of S1 and P1 are not equal. Only velocity of S1 and P1 along the tangent plane are equal because no slip is taking place here. Okay. So first what we must do, we must find the velocity of P1 by applying SRC between C and P1, and then equate the component of velocity of P1 along the string to be equal to V. Then we will get the value of Vc. Okay. But you can't say that this, because this S1 is moving at speed V, so this point will also move at speed V. You can't say that. That is true only when velocities of P1 and S1 are equal along common normal and also along common tangent. But velocity of S1 and P1 are equal only along tangent and not along common normal. So we can't say that if velocity of S1 is V, then velocity of this point is also V. That we can't say. But only velocity of S1 and P1 along tangent plane at this instant are equal. Okay. So now what we do, first we apply SRC between C and P1, and then equate the component of velocity of P1 along the string equal to V. Then we'll get the value of Vc. Alright. So SRC between C and P1. We take SP arrow C. C is the selected point, and OP arrow P1. SP arrow C, OP arrow P1. Now I draw the line joining C and S1. C and P1, sorry. C and P1. C and P1, alright. Now I give the velocity of C to P1. Velocity of C is Vc rightward. So I give Vc rightward to what? P1. Now I write down the sentence. Second rotation term. P1 moves in a clockwise circle with C as center and radius small r. For this I will give a speed omega r at right angles to this line CP1. Now one more thing. This angle is alpha. Corresponding angles. This angle becomes 90 minus alpha. By geometry, this angle also becomes how much? 90 degree minus alpha. This angle is how much? Tell me. 90 degree minus alpha. Fine. Alright. So this angle is also how much? By geometry, 90 degree. 90 minus alpha. So this is alpha. This is 90 minus alpha. Alright. Fine. Is it clear what I have said? So this angle becomes how much? 90 degree minus alpha. Now, I'm very sorry for the interruption, it just fell down, okay? I'll just attach it here, okay? So now, this is along the string. So this angle is also how much? 90 degree minus alpha. So along the string, we equate the velocities. Velocity of P1 along the string will be Vc cos 90 minus alpha. That is Vc sin alpha minus omega r. That is the component of velocity of P1 along the string. That is just equal to V. Also here, pure rolling is taking place here. So Vc will be equal to omega r, pure rolling criteria. So omega becomes Vc by capital R. So this omega I substitute here. Minus Vc into small r by capital R is equal to V. So on solving this, how much is Vc? Rv by r sin alpha minus small r. This is the required answer. So Vc1 becomes Rv by r sin alpha minus small r. Okay. This is the required value of Vc1, and this is therefore the required answer. So velocity of center C1 of double cylinder at this instant will be, Vc, not Vc1, will be Vc equal to Rv by r sin alpha minus small r. Alright. This question I have taken on 21st session of rigid body kinematics. This also I have discussed it. Fine. In one more session, I'll take up one more question on rigid body kinematics in the next session, and then the second chapter on rigid body kinetics will then be finished. After that, I'll pass over to the third chapter on rigid body kinematics. Okay. At last, I just the phone fell down, so I'm just very sorry for that interruption. Okay. Around 20-30 seconds, I was interrupted. I'm very sorry. Just don't cooperate. Okay. Fine. So I close it here.